Coming back to the lesson 34 activities. Please don't mind my cough drop. I'm trying to avoid coughing throughout this whole lesson. Okay, so we left off here at number 4. We've got a data table and the scatter plot given to us, and we have 3 choices for a model. And we're supposed to choose which one we think is the best and explain. Now, we don't have any technology to help us here, so this is modeling the type of question that you might see on the final exam, something like this. So we want to choose from these based on the shape of the scatter plot. So I think this looks pretty strongly exponential because it is curving upwards as it increases. And so a quadratic might also be a good model. But yeah, I think it looks exponential. So we're going to go with choice A. Quadratic might be good too. Because it also has the right half of a quadratic could look like that. But since we don't have technology to help us, we have to just make our best choice based on the scatter plot. So we'll go with choice A. Okay, so for number 5 here, we have 2 extrema, 2 turning points. There's one here and one here. And the end behavior, we can't see, there's only a limited amount of data, but it looks like the end behavior is right arm up, left arm down if the trend continues, with 2 extrema, which means that this would have to be a cubic. And then this one looks like the classic S-shaped curve. So we would go with a logistic model, which would be C here. Okay, so here we have a table that shows the population of various cities in thousands and the average walking speed in those cities. So you can see that as the population increases, it looks like walking speed increases too. We're going to make a quick scatter plot. I'll use Geogebra. And then pick a function that models the data well. We're going to write down the equation and the value of r squared and use our equation to predict average walking speed in a city of 100,000 people. So let's get Geogebra up. Okay, I'm going to make this a little smaller, make Geogebra a little smaller. So I can get the data entered here. There we go. Okay. So population 5.5, 14, 71, 38, and 342. And then walking speeds are 0.6, 1. These are feet per second, by the way. Okay, so I'm going to highlight my data, right click, create list of points. And then I just need to change my window to make this see all my data. So my x's go from about 5 to 342. So I need to show a lot more x values here. There we go. And then y's, a max of 2.2. So we'll go to maybe 2.5-ish. And I'm going to hide my labels on my points. Okay, so that looks pretty clearly logarithmic to me. It's increasing, but slowly. So let's do fit log list 1. Oh, it's a really good fit. Goes through almost all the points. Here's my formula. All right, so there's my formula, and it says I also want an R squared value and to predict the average walking speed in a city of 100,000 people. So R square, remember this is just a statistic that measures how well your model fits your data. And so we have to give it the list of points here. So that's L1. The function is f, and my R squared value is 1. That is, the closer to 1, the better the fit. I think it's probably just rounded that. So let's do rounding like to 5 decimal places. Yeah, we get 0.9987 is our R square value. And then I want to know in a city of 100,000 people, what's the walking speed? So I'm going to plug 100 into my model, and I get 1.74407. So those are my R square and my walking speed for a city of 100,000 people. Oops. All right, so just make a little note here. This one is R squared. It's so close to 1, which means it's a really good model. Fits the data really well. And this is walking speed for a city of 100,000. So this is F of 100. All right, we got one more example here. Table shows the US population in millions for various years. We're going to create a scatter plot. We want to fit both a linear model and an exponential model for the data. Write down both equations, both values of R squared, and then decide is either a good fit, which one is better. Use both equations to predict when the US population will reach 335 million. All right, so let's do this and this. Okay, my data is 1, 11, 21, and 41. And my Y values, these are US populations, 203.3, 226.5. And I messed something up because I should have 1, 11, 21, 31, and 41. There we go. All right, I'm going to highlight my data, right click, create list of points, minimize that. And now I can make this big. And I just need to adjust my window so that I can see this data. So X's go from 1 to 41, so I've got way too many X's here. Extend that to just past 40. And then Y's go from 200 to 300. I have not nearly enough Y's. Let's bring that down. There we go. And I think I'll actually do this. Okay, that's a good scatter plot. Hide my labels. Okay, so I'm supposed to fit a linear and an exponential function. Okay. So fit line for list 1. That looks pretty good. Let's do an R square for that. For list 1, matching function F. You get 0.9947. Really good fit. All right, let's do an exponential regression. So we want to do fit exp for list 1. fit actually doesn't look all that different. It's the blue there, and I want to do an R² for that. List 1 for function g, and that's 0.99813, so it is a little bit better. I'm just gonna take pictures of these. So here's my line. And my exponential. R² for the line. And R² for the exponential. All right, so there's my exponential model. Here's my linear model. This is my R² for the exponential. And my R² for the line. Just get these lined up here. All right. So is either model a good fit? They're both a good fit, definitely. And it's really hard to know which one is better. The exponential is a teeny bit better, but linear is a simpler model. So based on this picture, I wouldn't choose one over the other. Let's see, what did this data represent? US population, exponential, both of these are probably going to get big too fast. The exponential will probably get big faster than the linear, so I don't know. I think they're both good models, and I wouldn't use either of them to try to predict the future. Because probably what's going to happen is the growth is going to slow down. But let's use both to predict when the US population will reach 335 million. Okay, so go to Geogebra. I'm going to graph the line y equals 335. It's up here. And I want to know where it crosses with my two models, so I need to change my window a little bit. Hide the spreadsheet. Here we go. So I want to know where it intersects the linear model and where it intersects the exponential model. So in Geogebra, you can just use the intersect command. And then it asks which two objects are you looking at, and we are looking at the function f and the line h, and it gives me this point f, and then I want intersect the function g and the line h, and it gives me this point g. So I'm looking for the x coordinates of those 2 points because I know the y coordinates are both 335. So the linear model predicts 51.6 years, and the exponential model predicts 48.45 years. So 51.6 and 48.5. So 51.6 for the linear, 48.5 years for the exponential to hit 335 million people.